This is sort of a hybrid class. We have 3 technicians in a classroom, and then quite a number of you that are remote. I am recording this presentation so that it can be viewed later by yourselves and other technicians. This morning we're going to cover basic conveyor oven theory. At the end of this presentation, I'll send you a link to a 20-question quiz. And then after that one is done, we're going to go through the Middleby Marshall product line, and we'll have a quiz about it as well. If at any time you have any questions, just use the emoji icon and raise your hand, and I'll be happy to stop and address your questions. So, conveyor ovens, big part of our industry, big part of our business. Here's a number of manufacturers that we deal with. Before we get too deep into the conveyor ovens, first a little safety talk. If we're going to be safe, we have to know that our meters are operating properly. Please get in the habit of testing your meter when you're out in the field. Check it on a live voltage source so you know that you're reading voltage with it. To make your troubleshooting more efficient, always before you start to ohm something out, touch your leads together. Make sure that your leads will make your meter read 0 ohms. A meter that doesn't read voltage can cause a safety issue and injure a tech. Lockout tagout kits. T24U should issue lockout tagout kits to all of our technicians. If you don't have a lockout tagout kit, ask your manager. If you're not aware of what a lockout tagout kit is, basically it's a kit that'll have a tag like this and then other devices to lock out breakers, cords, and things like that to prevent you from getting electrocuted accidentally. Electricity can be fatal. Remember that it's not really the voltage that is lethal, it's the amperage. As little as 1/10 of an amp can be deadly. So you would definitely want to be careful when you're working with electricity. Always de-energize equipment before you remove panels from it. When we're checking our voltages, if we lose a leg of or a phase of voltage or potential on an oven that's 208 or 240, that is a single phase system, the oven's not going to operate at all. If we lose a leg on 3-phase, if the 2 phases still present are part of the control voltage, then the oven may still appear to operate. 3-phase motors, when they are not given all 3 phases, tend to hum and may bounce back and forth. And you'll lose 2/3 of your wattage capacity on a balanced 3-phase load, electric load for heating elements if you lose 1 leg of voltage. Never test components to ground except for purposes of safety. So when we're doing our testing, our troubleshooting, make sure that we're referencing neutral or another leg of electricity and not ground. If we have a break in a ground, or I'm sorry, if we have a break in the neutral line that is causing us problems, we're not going to see that if we're referencing ground. So only use ground to test to make sure there's no electricity present for safety reasons. There is a difference between neutral and ground. Neutral is designed to be a current carrying conductor, meaning that it's going to be energized and carrying current all the time. Ground is not normally designed to be a current carrying conductor. The only time a ground wire would carry current is when we have a short to ground, and that is only going to happen long enough for the breaker to trip, which is just a second. All right, so on to conveyor ovens. The first conveyor oven used in the pizzeria restaurant industry was originally called the Wonder Oven. It was invented by Harold Wells, who owned Black Body Corporation. The oven was constructed of 7 decks that used push-arm conveyor systems. It saw its first commercial use at Pizzuti's Pizzeria in Westland, Michigan in May of 1976. 2 years later, that company changed its name to CTX Cooking System. CTX is still around and is owned by Middleby Marshall. If you're in a Cheddar's or a Chili's, you're still seeing CTX ovens in the field. Conveyor ovens are basically great benefit of them is they're a time and a labor saving benefit, as well as giving the customer a very consistent product, because we're running product through a chamber at a constant temperature at a specific time, and that time never fluctuates. The first pizza chains to use conveyor ovens were Domino's Pizza and Pizza Hut. The mass production of these ovens was first done by Middleby Marshall. This is an old JS, this 200 series, early 200 series ovens, and they actually use a spark plug for an igniter. Conveyor ovens use a process that's known as air impingement, which reduces cooking time compared to deck ovens. Conveyor oven cooking is a lot more efficient for large volume pizza chains. Today, conveyor ovens are available in all sizes, from countertops to multi-stacked 70-inch cooking chambers. I was out Monday. You see the set of the 3 ovens on the right? We put a set of those in Monday down in southern Kentucky. It was quite a joy. I'm still tired. So air impingement performs 2 critical functions in the conveyor oven cooking process. First, the high velocity air created by the opening in fingers will push cold air away from the surface of the product, and then that high velocity air penetrates the product, which cooks it quickly and consistently. This consistent fast cooking can only be accomplished if the oven is installed, maintained, and operated correctly. When we install ovens, it's very important that we're going through all the proper procedures to make sure that everything is working as the manufacturer designed it, so that we're not dealing with cooking issues from early on. So what's impingement? In this picture, you can see what are called fingers. These fingers are made up of a couple of different parts. There are inner and outer baffles. There's a plenum. The entrance at the back is where the air is going to come through from the blowers. This air is then forced through this plenum, which is reduced in size from the back to the front to keep the velocity the same all the way across it. And that air is blown through these small holes, which increases their velocity to create the impingement effect on the product. We call these fingers, and we use just powerful blowers to create the air to flow through them. In the early years, customers had to adjust whatever their product was to match the standard generic finger, because manufacturers of these ovens just had a generic type of arrangement for their fingers. But as time went by and we had more companies like Domino's and Papa John's, the factories started doing test bakes of the customer's products in their factory so they could develop specific fingers that suited the product needs for each individual operation. Today, every chain has a specific finger arrangement to suit its needs. Finger placement is absolutely critical to the proper bake. One of the most common issues when you have a complaint about an oven not baking properly is the fingers are not installed properly. Any part of this arrangement being out of place greatly changes the baking characteristics of the oven. There are 2 things we think about when we're dealing with conveyor ovens. One is time and one is temperature. If you have a product that is not getting dark enough, that is a temperature issue. If you have a product that's not getting done internally, that's a time issue. So when you're dealing with bake issues, keep those 2 things in mind. So this is a generic finger arrangement for a Middleby 570. There'll be a decal on all the Middleby's. Most manufacturers are going to have some sort of decal that references how the layout of these fingers are. Looking at this, basically from left to right, you can see there are letters assigned to each of the fingers. And then as you go down into the chart, each of those letters will break down into the individual pieces of the finger. There are inner baffles, outer baffles. So you want to be able to make sure that all of those things are set up correctly and match this diagram. If you're on an older oven and you cannot find one in the oven, if you call the manufacturer, they'll be able to tell you for that customer what the arrangement should be. So we have inner plates, outer plates. They both have holes punched in them, and the number of holes and the diameter of holes is specific to every given chain. Improper installation of fingers and inner plates results in service calls related to bake issues. These calls are often preceded by an oven cleaning that require the oven to be disassembled and reassembled. So whenever you go out on a bake problem, the first question to ask your customer is, when's the last time your oven was cleaned? And if the answer is last night, you probably have a finger problem. If it's a new baking issue and the oven hasn't been taken apart for some time, you'll go in a different direction. But if the oven was cleaned last night, it's always going to be a problem with fingers. The most conveyors ovens consist of three basic subsystems. There's a fan or the main blower system. This is the system that's going to create the high velocity air that's going to cook our product. We're going to have a heat circuit. This system is used to heat the air that's used in cooking. This system may be gas or it may be electric. Thirdly, we're going to have a conveyor system. And this is the system that is going to move the product through our cooking chamber. So first, main blowers and fans. There's several components you're going to find depending on which manufacturer you're dealing with. Your blower may be started by a contactor or a relay. Unless you have a digital control, you may have a blower switch that turns on the main blower. There are typically going to be some sort of fuses or circuit breaker protection in the motor circuit that may cause issues. Newer ovens, we're seeing variable frequency drives that are running the motors. We may have direct drive motors, or we may have motors that are belt driven and that have pulleys and bearings in their systems as well. All conveyor ovens, except for CTX, will have at least one main blower motor. While many of these motors are single phase and run off line voltage, more and more manufacturers are using inverter rated three-phase motors. The use of VFDs allows this application on single phase ovens. Strict attention to motor rotation must be paid when you're replacing a motor or troubleshooting bake issues. If your rotation is incorrect, you're going to have poor baking characteristics. VFDs were, and I'll talk more about these in the Middleby section. Some people call them inverters or a variable frequency drive. They're able or capable of taking a single phase input and creating a three-phase AC output to run a three-phase motor. And so if two of those motor leads get reversed, it changes the rotation of the motor. This is a picture of a Middleby 360. 360 is probably by far the most common pizza oven that's been out over the last 30 years. There are still thousands and thousands of these things in operation. You can see that this is a double stack of ovens. Each oven has two motors. They use the same motor in all four locations because the motors are reversible. But as you can see, there is a clockwise on the upper right and a counterclockwise on the upper left. So what's different to change the airflow is the blower itself. The wheels of the blowers are always direction specific. They have vanes that are kind of like a cup, and they scoop the air and distribute it to the finger assemblies. A good indication of a blower wheel that's running backwards is low amp draw. Always remember that you do not know who serviced this equipment before you. Years ago, I went on a call that I had to drive about 2.5 hours to. Another company had changed the blower motor and it was running backwards. So it was a very easy call, but it does happen. If you have two of the same motors in the same oven, your amp draw should be very close, like within 0.2 tenths of an amp. If you've got an amp or two difference, you probably have a direction issue. If you have one, you should never be more than maybe like 0.2 of an amp difference. They're both running in the same, in the correct direction. If you have one that's going backwards, it's going to draw significantly lower amps. So a lot of manufacturers use pre-assembled blowers, and they'll come from the factory they're ready to be installed. But you always want to verify the rotation is correct when you replace a motor, especially if your customer's having a bake issue. On a motor like this, there'll be a little diagram on your data plate. And on this motor in particular, to reverse direction, we reverse the red and the black wire. It's that simple. In addition to being reversible, a lot of these are dual voltage. So you want to pay close attention to what you're doing when you're installing them. Always double check your connections before you apply power to the diagram on the motor data plate as a reference. Also, always make sure you know what your input voltage to that motor is before you start wiring the motor. On this motor, you see these two brown wires. These brown wires are connected to a micro switch. And this switch, called a centrifugal switch, is actuated by centrifugal force that's created when the motor spins. So these switches are wired into the unit to prevent the oven from heating unless these switches close. So on a direct drive blower, the centrifugal switch is the most common method of proving that we have rotation. They're always going to want to prove that there's rotation before they energize a heat circuit. Some main blowers are going to use run capacitors. If you have a run capacitor that fails, follow these steps. First, make sure that the motor incoming voltage is correct. Second, check the motor for open or shorted windings. Third, make sure the motor will turn. If all of these things are correct, go ahead and replace the capacitor with one that matches the microfarad rating exactly and meets or exceeds the voltage rating. So your microfarads on run capacitors have to be exact. Your voltage rating can be the same as the one you have or higher, but you cannot go down in voltage rating. Once you have the new capacitor installed, energize the unit and check the motor amp draw. If your amp draw compared to what your data plate says it should be is correct, then let the customer know that if that capacitor fails again, the motor should be replaced. If the amp draw is high compared to the specs on the data plate, go ahead and do a quote for the motor and blower replacement. Some main blowers are going to be belt driven and use pulleys. And these systems typically incorporate some type of a bearing, as well as some type of shaft to connect the pulleys to the blowers. Something has to energize our main blowers. This is usually going to be a contactor or a relay. This is the switch that basically energizes that motor to bring it on. Typically, these coils operate off of line voltage, but they can also be controlled by a low voltage, like a 24-volt circuit, depending on how the manufacturer is designing their oven. If you're not getting voltage to a motor or voltage to a contactor, the coil, you may have a problem with either mini breakers or fuses or even thermal overload protection that helps protect the motor and controls. So if you don't have voltage at a motor, trace back through your circuit and see what's preventing it. 2006, Middleby Marshall introduced variable speed frequency drives or an inverter. These power a three-phase motor from a single-phase supply. The primary reason for these to be used is energy efficiency. Being able to lower the frequency the motor operates at during off-peak times, the motor uses less energy and increases the efficiency for the customer. One of the most important things in a conveyor oven, if it's equipped, is the cooling fan. These fans are used to bring room temperature air through the oven over the controls and motors to keep them cool. They become blocked or fail to operate, you can have much more costly failures. Anytime you're working on any oven that has cooling fans, which is pretty much all of them, make sure the covers are clean, make sure that the fans are operating correctly. The fans are always going to be bringing air in from the outside and pushing it into the oven. It is not uncommon for technicians to install a fan in the improper direction. On this fan, you can see that there's arrows that tell you which way the airflow is going. On conveyor ovens, we want that airflow to be going in towards the controls and the motors. Generally speaking, these fans are going to run anytime the unit is on. These fans also are rated for voltage. You must make sure that you're getting the correct voltage replacement fan when you're replacing these. The easiest way to do that is to make sure you order the OEM, but it's still a good idea to always check the voltage before you install anything to make sure it matches your supply voltage. The main blower motors and controls must be kept cool by axial fans. Here's a picture of a very, very dirty cooling fan. This cooling fan is probably so bad that if you have another fan, there's no reason to clean it, just replace it. You should check cooling fans on every service call. Some cooling fans will have a filter material covering them to reduce the amount of contaminants like dustinator. Dustinator, if you've ever worked at a Papa John's, is a very fine cornmeal product they use to roll out their dough when they're making pizzas. It gets into the air very easily and will suck into these filters and clog them. And this also will create high temperatures in your control compartment. You can remove these very easily, wash them off with hot water, let them dry a little bit before you reinstall them. This is also something that if the customer wants to order a pack of 8 or 10 of these, they sell them at Parts Town. They could be changing them themselves if they're not on a PM program. Main blower motors are also going to incorporate what's referred to as heat slingers or fan blades. These use the rotation of the motor to move cooling air across the motor when it operates. So the fan blade that's on the bottom left is a fan blade that would mount to the end of a motor on a shaft, and as the motor turns, that fan blade is going to blow cool air across the motor. The one on the right is called a heat slinger. It's just a little cast aluminum plate. The vanes on that, this slides on a motor shaft, and the vanes on that point toward the motor. And as the motor spins, those vanes create an airflow across the motor to keep it cool. Heating circuits. There's a lot of different components you might see in heat circuits. We're going to have gas valves, combustion blower motors, igniters, flame sensors. For electric ovens, we'll have contactors, heating elements, temperature controls. You may see hot surface igniters, ignition modules. Most conveyor ovens utilize natural or LP gas to heat. Some are electrically heated. Typically, smaller ovens are electrically heated. The small countertop ovens we see made by Lincoln and TurboChef are typically electrically heated. They're used mostly in convenience stores. and that don't have access to natural gas, and oftentimes don't even have exhaust hoods. The components in gas-heated units typically consist of an electronic ignition circuit, a solid-state temperature control circuit of some type, and then either a high-flame solenoid or a modulating gas valve. This is the gas train on a 500 series Middleby oven. These gas trains may operate on 24 volts, 120 volts, or 208 volts. Most conveyor ovens, larger conveyor ovens, use what's called a power burner. A power burner uses a combustion blower motor, which pushes primary air into the burner, which makes it more efficient. Here's an example of a combustion blower motor. This one in particular is rated at 230 volts. In the 300 series Middleby, it would be a 120 volt motor. And you can see that there is an air shutter on the left side of that blower. And that air shutter is what controls the amount of primary air we introduce into the burner. Yeah, one of the guys here in class made a point. That air shutter does not always come with a new motor. So if you're replacing one of these motors, you may have to take the air shutter off the old motor and put it on the new motor. So just make sure that when you're done, the motor looks like it did when you started. The air shutter can be adjusted to fine-tune flame current on most ovens with a disc type, like that's shown here. You're going to start at about a 1/4 inch open, and you can increase or decrease until your flame current's where it's desired. You should only adjust the air shutter after all the other checks we're going to talk about have been done. So air shutter fine tuning is the last thing we do. If we know that our burner and our igniter and our sensor are clean, we know we have a good ground circuit, we know we have good gas pressure, but all the other things have been checked. If you have low flame current, you can make some adjustments to an air shutter. This is a power burner. It's a variation of an old oil burner. This burner does not produce a well-defined flame like you might see on a fryer or a grill. This is a big hunk of gas getting blown into a very large opening inside the plenum of an oven. So do not expect to see well-defined flames on large ovens. Most of these burners are going to have some type of metallic disc that's called a target at the end of the burner. That target is there to help spread out the flame and help distribute the heat. It also has some effect on flame current by keeping some of the flame back towards the burner. So if you have a missing target, that can cause low flame current issues as well. One of the most critical factors for gas conveyor ovens is gas pressure. And I really can't emphasize this enough. I've seen so many problems over the years on pizza ovens that came back to gas pressure or gas volume that had not been checked. So we typically are going to look at 3 pressures. The first pressure we're going to look at is incoming pressure. And we're going to look at static pressure versus dynamic pressure. Static pressure is the pressure before we turn the appliance on. So I take a manometer, I hook it up to the incoming gas pressure, and before I turn my oven on, that's my static pressure. Once I turn the appliance on, now I have what's called dynamic or running pressure. Typically, I don't want to see more than about a 20% drop between static and dynamic. Most manufacturers are going to tell you you need to have a minimum of 7 inches of water column on natural gas coming in as a dynamic pressure. If you get much more below 7 inches, you may start to run into gas volume problems. The second pressure we're always checking is manifold pressure. Manifold pressure is the pressure that we're going to regulate out of our gas valve, and this is the pressure that our burner is actually going to operate on. It is usually about 3.5 inches of water column, but you always want to verify that with your data plate. There are some ovens out there that will run at 4 inches of water column. The last gas pressure adjustment is pilot pressure. This varies from manufacturer to manufacturer, but typically speaking, your pilot pressure should be, it's typically a little bit higher than manifold pressure. If I have an oven that's running 3.5 inches of manifold pressure, I will run about 4 inches of water column on my pilot. That too can be adjusted depending on how your flame current is reacting. If you have too low of pressure, you'll tend to have ignition lockout issues. If you have too much pressure, you may have a situation where your burner doesn't ignite because the module never sees the flame current. Just a little bit over what your manifold is typically. So these are different types of manometers that are used to check gas pressure. They may be a water manometer like that one on the right. You may have an analog gauge, or you may have a digital multimeter. There are a couple of the Middleby Marshall ovens, the 540, the 640, 740, the 40-inch range, that you will have to have a digital manometer to set the pilot pressure, because it runs between about 0.4 and 0.5 inches of water column. And you're just not going to see that accurately on a water manometer or a gauge manometer. Step-down transformers. Most ovens are going to have a step-down transformer, and that is going to be used to power ignition modules. The ignition modules are typically going to run off of 24 volts. There are some modules out there that will use a combination of 120 volts to power the module and 24 volts to switch voltage to a gas valve. All right, so once our combustion blower either actuates a centrifugal switch in it or a pressure switch that approves the rotation, the next component to be energized is an ignition module. And this ignition module may utilize direct spark, or it may have a hot surface igniter. Most of the world is direct spark. The only oven we see out there that is still using any hot surface ignition is Lincoln. The 1100 series Lincolns and the 1600 Lincolns are still using hot surface igniters. So this ignition module is going to receive an input voltage or a call for heat. Once the call for heat is sent to the ignition module, it's going to energize a gas valve and create a high voltage spark at the burner or pilot. Once the flame is present, flame sense or rectification can occur. And at that point, the ignition module will send voltage to the main valve part of the gas valve to allow full flow of gas. So flame rectification. The way flame rectification works is that an AC voltage is sent down our sensing wire to our flame sensor. The flame sensor is much smaller than the pilot assembly. And what will happen is the AC voltage, basically through an ionization process, uses the flame as a load. And the flame creates a current. Once it sees a path to ground, the primary condition is whatever that path is, that grounding path is, must be larger than our flame sensing, our flame sensor itself. So once that happens, we get what's called flame current. We measure that flame current in microamps. Most Middleby products are going to want a minimum of 2 microamps. Some ovens will have modules that require as little as 8 microamps. Traditionally, conveyor ovens use either a constant pilot or a bypass flame. So there's always an ignition source at the pilot. And they'll either use a high voltage, or I'm sorry, a high flame solenoid that's just an on and off. The valve you see here is a 24-volt valve that Lincoln and other manufacturers use. This valve is used in conjunction with the 24 volts the ignition module uses, and it's powered by it. There's a little port that allows for a bypass tube that goes down to the burner so that it always has a pilot as this unit cycles on and off. Because Lincoln is using on some other ovens, because they're using hot surface igniter, they have to have that pilot there so that every time the main gas valve is energized, the burner can light instantly. Without that pilot light being there, they would have to go through the 30 or 40-second process of re-energizing the hot surface igniter, and this would cause a temperature drop in the oven of like 40 or 50 degrees. If you're ever working on a Lincoln oven and the customer says that it drops 40 or 50 degrees and then it heats back up, get a hot surface igniter. That's going to be your problem. I've never had much luck cleaning the sensors on these hot surface igniters. You can try to do that. The problem is they're very delicate. So it's always a good idea to have a new one with you before you try and pull this one out. You also, on a lot of the Lincolns, will have to pull your conveyor oven to get the burner to come all the way out. So these constant pilot systems are reliant on clean orifices, clean pilot assemblies, and a good ground sensing path. Must have the correct gas pressure for the pilot. If you have low flame current, low gas pressure, or a clogged orifice, or a dirty pilot are the most common issues in conveyor ovens. So these are just some basic things to make sure you're checking when you're looking at ignition problems. Pilot gas pressure. These adjustments are very important. You're typically going to see a little T on many of the ovens where there's a tap like this that you can put your manometer on. If you have too low of a pressure, you may have sooting. And if you have too high of a pressure, it may prevent your pilot from even igniting. This pressure is controlled by an orifice in the pilot tube, or there may be a needle valve that you adjust on the gas valve itself. When we get in the middle, I'll show you how that adjustment works. A lot of blowers will have a little viewpoint. That viewport is only going to tell you that you can see a flame. It's not going to give you much of an indication of the quality of it. Flame current is really the only measurement of the quality of flame on a burner like this. So the next component in the heat circuit is the gas valve. There's usually two valves in each oven. One works in conjunction with the ignition module, and then one in conjunction with the temperature control. The one you saw a couple minutes ago works in conjunction with the ignition module. It's a 24-volt valve. And then we'll usually have either a modulating valve or some type of high voltage cycling solenoid that is controlled by our temperature control. So these are two examples of the first type that work with the ignition module, and they will shut the flow of gas off to the burner if the ignition module senses low or no flame current. Basically, this valve acts as a safety. The flame current is good. It's always energized when the unit is on. The second type of valve is used to control temperature. We refer to this valve as a cycling solenoid because it opens completely when there's a call for heat, and then closes completely when the call goes away. These valves can operate at 120 or 230 volts AC. If you see one of the valves in the bottom right with the black and white wire, that's a 120 volt valve. If you see one with a yellow and black wire, that's a 208, 230 volt valve. This valve is called a modulating valve. Modulating valves typically operate in the range of 0 to 20 volts DC. The higher the input voltage to the valve, the further it is open to allow more gas flow. As demand increases, they receive the input from an amplifier board or other temperature control device. So basically, this valve is always opening and closing. When there's more of a demand for heat, it will open more. As that heat demand decreases, it will close more. Most of our controllers the higher the voltage on the modulating, the text question is on the modulating valve, how does the voltage work? The higher the input voltage to the valve, the further it is open. So the more gas flow we get. As that voltage is decreased, the valve closes and we get less gas flow. In case anyone didn't see the email I sent out a week or so ago, there's a copy of this, a PDF version of this presentation and all the other presentations for conveyor ovens, as well as a lot of other documents now in Alert in a folder called Conveyor Oven Training. So if you ever want to go back and reference any of this stuff, it's there for you in Alert or on your tech docs in your phone. So sensing temperature. Controllers on conveyor ovens will vary widely. Some will have one control for temperature and a separate one for the conveyor, or one that controls both. So you may have two boards, one for the conveyor, one for the heat, or you may have one board that does both the conveyor control and the heat. But almost all the conveyor ovens use either a type J or a type K thermocouple. The type J will have a red and white wires. The type K will have a yellow and red wire. In both cases, the red wire is the negative. Yeah, red is always negative. Electrically heated conveyor ovens use cow rod type elements. They come in many different shapes, sizes, voltages, and wattages. The elements have to be powered by a contactor, a solid-state relay, a mechanical relay, or a combination of these. Typically, if there's a contactor, there'll be an SSR that's also utilized. The contactor acts sort of as a latching contactor. Then the SSR will do the cycling. All conveyor ovens are going to have some type of over temperature or high limit protection. The limits might be built into a controller. They can be mechanical thermostats, or they can be separate solid state temperature control. The solid state control at the bottom right is used by Middleby, and it will have a separate thermocouple that is sensing temperature in the cooking compartment. Most conveyor ovens will use some type of method to cool the oven down once the user shuts it off. This can be done with a solid state timer or by a control looking for a specific temperature, or even a snap disk thermostat. Conveyor circuits. There's a number of things you're going to see in conveyor circuits, including conveyor motors, speed control boards, what are called Hall effect sensors or pickups. We're also going to deal with conveyor belts, conveyor chains, and conveyor sprockets. The conveyor is the mechanism that moves the product through the oven cook chamber. It's a flexible belt that wraps around a frame and has rotating shafts at each end. Different manufacturers stress this more than others, but the belts should have a direction of travel. As you can see, there's a hook at the end of these belts on each side, and it's best to have that hook traveling in this direction so it doesn't snag on anything. You can also see there's a series of what are called master links, the little red connectors. And those master links are what hold our belt together. They allow it to be taken off of the frame. Conveyor belts can be a single belt, or you may have two belts that can be used for what's referred to as a split belt conveyor. The shafts for split belts are different than a single belt, and they'll also have two motors, two conveyor motors, and two speed controls. The conveyor is typically chain driven. There are some smaller ovens that will use a rubber or metal coupling and not have a chain like this. Chain tension on these ovens is very important. We don't want the chain tension to be sloppy or the chain will skip. And we don't want the tension to be so tight that it causes premature wear of bushings and bearings. The sprockets used have a set number of teeth on both the drive and shaft sprockets. This gear ratio must be correct for the controller to achieve the desired belt speed. I'll show you later a universal kit for one of the ovens that comes with a number of different gears. And if you don't get the right number of gears, the gear ratio correct for your oven, your belt speed will not be correct. Drive chain tension and sprocket alignment are also extremely important. Misaligned sprockets will result in skipping and premature chain and sprocket wear. Always check chains, sprockets, and other conveyor parts for excessive wear on each service call. I mentioned a number of things that we should check on every service call. Conveyor ovens are sort of a big picture thing. So cooling fans are important. The chains, the sprockets, the gears are all important. Gas pressure is super important. So just be aware that when you're working on conveyor ovens, it's a big picture process. You have to look at everything. You can lubricate these chains if you have some type of a high temperature food grade oil. The shaft sprockets are there to support the belt, and they also have to be properly aligned, and they have a little set screw so they can be tightened. If they're misaligned, they can cause the belt to ride off to one side, then your belt snags, and then you have a whole different issue. Conveyor motors, especially older conveyor motors, operate on a DC power supply. The older DC motors contain two of these items that are called brushes. They mount at the end of the motor on opposite sides. They are a wear item. They wear past about half of their original length. You might get erratic motor operation. Customer will say, conveyor will run for 10 minutes and then stop and then start by itself. If you have brushes in a motor, take them out. We do not want to use CO2 to blow out DC motors. We can use compressed air or we can use nitrogen. CO2 has been proven to, because it's coming out of your jug as a liquid, basically like a refrigerant, it can damage the varnish on the motor windings inside the motor. So avoid using CO2 to blow out the carbon from these. DC motors are extremely powerful. And because they're so powerful, there's going to be some sort of a over amperage protection to take it out of the circuit. This is usually going to be a fuse or a mini breaker, or there may be some kind of protection in the motor itself. Newer motors that we're seeing are brushless DC motors. They're becoming more and more popular. With the advent of cheaper computers and power transistors, it became possible to basically turn the motor inside out, eliminate the brushes. In a brushless DC motor, the permanent magnets are on the rotor and the electromagnets are moved to the stator. DC drives. All DC motors are going to have some type of a DC controller that's going to be looking at what the desired time has been set by the customer, and then it's going to create a DC voltage output to the conveyor motor. As that DC voltage increases, the motor will turn faster. When the DC voltage decreases, the motor will turn slower. In order for the speed control board to know how much voltage to send to the conveyor motor, it must first know exactly how fast the user wants the motor to go. This is achieved through a user interface of some kind. So basically, this is a little, I still call it a thumb wheel, but it's a digital display and allows the user to set the time in minutes and seconds that they want their oven to run at. So once we know what the time is that the customer wants the product to run at, we have to have some method to tell us how fast the motor is actually turning. This is typically achieved through a device that's most commonly the Hall effect sensor. Some people will call this a pickup or a tach generator, but the Hall effect is basically what it is. And basically the Hall effect is the production of a voltage difference across an electrical conductor transverse to an electric current in the conductor, the magnetic field perpendicular to the current. That's a really fancy way of saying it looks at polarity changes in a magnet. As we go from positive to negative, and we have a specific number of poles on a magnet, the Hall effect is there to interpret that signal, send the signal back to the board, and then the board knows how fast the motor's going. This is a closed loop system. As we look at this, at the bottom of it, you can see that there is, we have a transformer and we have two leads that are going to our AC. This AC voltage is the input voltage to our controller. At the top left, we have an arm plus and arm minus. This is the DC voltage out to our conveyor motor. And then over here to the top right, we have a 4-pole magnet that is connected, is being sensed by our pickup. There are 3 voltages or 3 terminals for the pickup. One is common, the second is +5. When we look between common and +5, we're going to see 5 volts DC. When we look between common and count, we're typically going to see about half of that voltage, or about 2.5. The purpose of checking this is really, number one, make sure you have the output voltage from the controller if your oven is not controlling speed properly, and then to make sure you're getting return voltage. A lot of times if we're seeing the +5, but we're not seeing our common and count return voltage, it may simply be that our sensor is too far away from the magnet. Most applications, the sensor should be no more than the thickness of a business card away from the magnet. Some systems use other mechanisms to sense motor speed, but we'll cover those when we do manufacturer-specific training. And the last item in conveyor oven theory is cook time. So in order for us to know that our conveyor is traveling the correct speed, we're going to simply put a pan into our conveyor oven, and we're going to time from the leading edge in of the tunnel till it comes to the leading edge out of the tunnel. So the front edge of the pan, you start your timer when it goes into the tunnel, and you stop your timer when it comes out of the tunnel. And that is cook time. And that's universal to all manufacturers.